Welcome back, ladies and gentlemen. Today we're talking about friction, and we're going to cover a lot of detail. Basically, friction is a force. Let's start with some basic stuff, maybe kind of like a definition here. It's a force. It always opposes motion, or I'm going to say the tendency to move. And this is kind of a subtle thing. The tendency to move. So when two surfaces are in contact and this one surface is sliding past the other, there will be friction. And when two surfaces are in contact and they're not moving, but they're so-called this tendency or attempt to move, then there will also be friction. In that case, friction would be preventing that motion. There are two kinds of friction. There is kinetic friction, where things are moving. And the typical symbol, traditional symbol, lowercase f sub k. There's also static friction, which is stationary, no movement. And this is lowercase f sub s, typically. These are the symbols your book uses, I believe. All right, well, we're going to look at each of these kinds of friction separately and see what they can give us, see what we can figure out. So kinetic, let's look at this first. Friction between two moving surfaces, there's a relationship. This kinetic friction is equal to this thing called the coefficient of kinetic friction multiplied by the normal force between the two surfaces. And that's it. It's a very simple equation. But let's look at what's going on. Because friction is a force measured in newtons, normal force is measured in newtons. If we isolate this coefficient of kinetic friction, we'll realize that it has no units. The newtons sort of divide out, and it's a unitless number, just that's why it's called a coefficient. But it is the coefficient. You probably want to write this. Coefficient, I can spell, I swear, of kinetic friction. Okay, so what about this? It is unitless, has no units. It is usually a value between 0 and 1. And what it depends on, this quantity, this is an important part, depends on the types of surfaces in contact. The types of surfaces. So we have some basic information about this coefficient of kinetic friction. And so what this tells you, if it only depends on the types, only depends on the types of surfaces like rubber and concrete, wood and porcelain, or leather and paper, any two kinds of materials, any two kinds of surfaces, then what does it not depend on? So this is not, there is motion taking place, but it does not depend on the relative speed. These things could be sliding slow or fast, and the coefficient of kinetic friction will be the same. It also does not depend on the amount of surface area in contact, which may be a little counterintuitive, but it doesn't. So having more or less surface area in contact does not change this coefficient, and therefore, if that were the only difference, you would have the same amount of kinetic friction force as well. All right. Well, this is all good, but let's look at how we can apply this knowledge, right? So, an example of what could be happening. We're going to have an object. Here's an object, right? And we're simply going to push it along. So I'm going to apply a force to this object, and I'm going to get this force moving at a constant velocity, if I can, like that. Now, I was applying a force to it. Why did it not accelerate? Well, the reason why is friction. So let's look at that situation. What does this mean for us? So we have this object, right? This round thing. and we applied a force to it, and we got a velocity in this direction, but we had a constant velocity, so acceleration was 0, right? Acceleration equals 0. This is a situation where you have constant velocity, and that's right there a subtle thing. Constant velocity, same speed and same direction. This is an example of what's called translational equilibrium. Translational, oh my goodness, equilibrium. It's a word that might come up, ignore that little mistake. Basically means translational. It's translating to a new location. It's moving. Linear motion. Think linear motion. And equilibrium. Well, balanced. Things are balanced when equilibrium is our condition. And so, what was balanced? Well, the forces had to be balanced. Let's look at that now. Free body diagram of our situation. Now, the view a moment ago was from above our object. This free body diagram will not be from that point of view. This free body diagram will be from the point of view of the side. And the reason is, from above, I'm going to have a hard time representing a force that is downward, because downward is like this, into the paper. And a force upward is like this, out of the paper. And I can't really draw those well on a two-dimensional diagram like this. Here's my y-axis, x-axis. What are the forces acting on this thing? Well, of course, there's this force that I applied. What else is there? There's weight. This thing does have mass, so let's look at this. Let me list the mass of this object. It was just 10 grams. That was it. Okay. And so there is weight, and if I know the mass, I can find the weight. I know that. And there's also a normal force. The surface is holding it up. Okay. Now, I understand already that the object was not accelerating up or down into the paper. And so the sum of those two vertical forces would be 0. But so here we go, I should write this down. When I do this now, I also have a friction force which opposes the motion. The motion was to the right. I'm going to make that the positive direction, by the way, which I have here, positive x. But I need an arrow going this way in my diagram. I'll get to that in a moment. First, I'm going to start by what's called a second law statement, sum of forces in the y direction. And a second law statement basically says, well, the sum of forces, which is equivalent to saying the net force, that is equivalent to a mass times an acceleration, in this case an acceleration in the y direction. Well, I know that my acceleration in the y direction is 0. So, the y equals 0. I can observe that. Therefore, sum of forces in the y direction. If A is 0, the sum is 0 here. But what are those forces? Well, those forces are normal force up, weight down, equals 0, and therefore normal force equals weight. Okay. But what about the x direction? Okay, so this. I'm going to do another second law. Let me highlight this a little bit. This is a second law statement, Newton's second law. Maybe I don't have to include that part, but this right here is the beginning of all kinds of knowledge about the situation. Let me do one for the x direction, sum of forces in the x direction. So this is equivalent to mass times acceleration in the x direction. Okay, but I also have, in this situation, it's translational equilibrium. The acceleration in that direction is 0. The x is 0. So therefore I can say, well, the sum of forces is also 0. So force in the x is 0. What are those forces? That's my force applied. And in the negative direction, I have my force of kinetic friction. There it is. And the sum equals 0. Therefore, my applied force equals that force of kinetic friction. Okay. Now I haven't come to, oh, let me do it, I've highlighted this guy too. I haven't come to really any more understanding than this, then, well, the whole thing is in equilibrium. The whole thing, there's no acceleration anywhere in any direction. But my free body diagram is still incomplete. But now I know that the friction force is equal to that applied force, so I have to draw it the same length. There we go. Now, my free body diagram is complete. And I have my second law statements. Newton's second law, F equals ma, is basically this, but I broke it up into separate x and y directions. Very important that you do that. Forces are vectors. Okay. Well, what if I have a more specific question about this, right? Here's sort of like general information. What if I have a very specific question? What force is needed to produce constant velocity in this situation? In the same situation where the object's be pushing across the surface of the paper. By the way, before we get to this, this is something that really stumped people for hundreds or thousands of years. This is counter to our what we can easily observe. Look, I can observe that not moving because I'm not applying a force to it, and as soon as I apply a force to it, I observe it moving. Excuse me. When I stop applying the force, the object stops moving. My conclusion is easy. It won't move unless I'm applying a force. That's it. But that's not what happens. If there were no friction force, imagine this. If there were no friction force, and I applied a force to this thing, and I got it up to some speed because I accelerated it, and I got up some speed, and there were no friction, then I could stop pushing it, and it should keep going at the same speed in the same direction. But that is not what we observe. Counter to intuition. Now, let's get to the answer to this question. What sort of force is needed? What is our applied force required in order to do this? Well, the applied force is overcoming friction to maintain a constant velocity. So if I can find the value of that friction force, then I can find my force. But the friction force, I know, depends on this coefficient of kinetic friction between the surfaces, which is just, it's like a constant. If you know the surfaces, you know that coefficient. Typically the kind of thing you look up or you're given in a problem. Normal force, so I have to know the normal force to know the friction. Well, I know that my normal force is equivalent to my weight. Well, so I need the weight. And I know that weight, well, what is weight? Weight is mg. And I know the mass, and I know g. You can see where this is going. Let's get this rolling. Here's how I would approach this. Weight is mg. So I have a mass of 0.010 kilograms. I converted from grams to kilograms, and g is 9.8 meters per second squared. Okay. And so my weight is 0.098 newtons. And so, okay, right away, notation. I have an N for newtons, and I have an N for normal force. So if it's a normal force, I will always have that arrow across the top of it. Okay. Now, but from this, I know, because I know the weight, I know the normal force is the same. Okay. Well, okay, now I know the normal force, and I know that if I multiply normal force times the coefficient of kinetic friction, I can find the amount of friction force. So between these surfaces, between the plastic and the paper, what's my coefficient of kinetic friction? Well, in this example, we're going to go with 0.30, and this is kind of a typical thing. It's plastic on paper. Right? Well, okay, well, from that and that, so I can do a calculation for the amount of friction. So, okay, times the normal force. So this is 0.30. Remember, no units on the coefficient of kinetic friction. My normal force was 0.098 newtons. How much kinetic friction is there? It's a small number, 0.294 newtons. Well, I understand from my work with free body diagram and Newton's second law that my applied force must equal the kinetic friction in order for the thing to move at a constant velocity. So, from this, I have the answer. I have how much force I need to apply in order to move that object, that plastic piece, at a constant velocity. That's it. So you can see some preliminary work I did from Newton's second law, and this just gave me some relationships that I ended up using to get to my answer. Is it unimportant? No, it's very important. Can you skip this? Well, you can try to do it in your head. Excuse me. I would not try to do this in my head. I would not. Do not get lazy. Write this down. Partly because, what if you mess this up or you forget how to do this? At least you have this. And this is probably worth points to you. So is that diagram, by the way. All right. So we could find out that force required if we knew the mass. And what else did we have to know? We had to know this coefficient of kinetic friction. All right. Now, that's kinetic friction where things are moving. What about static friction, right? Where's page 3? Here's page 4. Well, okay. Let me pose to you several different situations. No longer using the paper. I'm going to use this. It's a clipboard, fiber board. I'm not sure what you would call it. And if I just leave this flat, then is there any friction taking place between the plastic and the clipboard? And the answer is no, because there's no tendency for this object to move anywhere. There's no reason it would move. There's a weight downward, there's a weight upward, gosh, a normal force upward, but there are no other forces acting on it. So no friction force is developing there. Instead, what if I tilt this? If I tilt it far enough, you know what's going to happen, right? Well, we'll get to that. Hang on, patience. Let's talk about static friction. Okay, static friction occurs between two surfaces where no motion occurs, but motion would occur without the friction present. This is the tendency to move. So it still opposes the so-called attempt for the surfaces to slide past each other. The equation for this guy is subtly different. Oh, that's not an equal sign, right? Coefficient of static friction times normal force. So why the less than or equal to sign? Because the static friction force changes depending on the amount of force that would tend in quotes to move the object. But up to a maximum amount, there is a maximum static friction force possible that is equal to the coefficient of static friction times the normal force. But that doesn't mean the static friction force is always at that amount. It could be less. And in fact, in this case, it is 0 with this thing flat. Just leave it there. And there's no friction force at all. If I tilt this a little bit, well, it would tend to slide down. There's a small component of gravity in the direction of this plane, and this would tend to slide down, but friction prevents that. Is that friction equal to the maximum amount? Probably not, because I could tilt it further and it still doesn't slide until I get far enough, right? It's also clear if I bump it, it changes things. But so the static friction will not always be equal to the maximum amount. Make sure you understand that. But no larger than that, the maximum This coefficient is more or less just like the kinetic coefficient of friction. It is also unitless. It's almost always greater than. The coefficient of kinetic friction is almost always larger than that guy. Interesting there. What that tells you is that static friction will almost always be larger than kinetic friction. Once it's sliding, it's easier to keep it sliding than it is to get it sliding in the first place. So again, this coefficient of static friction depends on the types of surfaces. It does not depend on the amount of surface area in contact. And since there's no motion, it doesn't depend on speed at all, right? This one ranges from 0 to, it can go well past 1 in value. And there are situations like that. But let's check out a different example now. You saw me with the clipboard. And you saw that eventually, if the clipboard got steep enough, it would slide. So with the clipboard horizontal, with the surface horizontal, how much static friction is there? There is none, because there's no tendency for it to slide. It doesn't. There's no opposition to a tendency that isn't there. But if I angle it a little bit, okay, here's an angle, and it's sitting here. Now it's not sliding yet, but there's a small static friction force. As that angle theta, I should label it something, as angle theta increases, what happens to the static friction force? Then static friction also increases. Sorry, that got to the edge of the paper. Now there will be a maximum value that the static friction can achieve. And at some point, at some angle, you increase theta enough. This thing is like, it's about ready to go. It's sort of on the edge of going kinetic, man. So at this so-called critical angle, your static friction force equals coefficient of static friction times normal force. Okay. And the object is just about to slip, just about to go. All right. So we got to look at a situation like this. And there's an interesting thing we can do. We can ask ourselves a question that will tell us about the coefficient of static friction between these two surfaces. Let's check that out. And then that'll pretty much wrap this video up. So we have the situation. Angle theta, object, about ready to slide. Here's our question. What is the coefficient of static friction between these surfaces? Can we tell? Well, okay, the mass of this thing is the same. It's that plastic piece. So just some information. Mass is still 10 grams. And so let's see what we can work out. Okay, wait. We know we have forces acting on this object. There's weight, right? There's a normal force. Now, normal force is angled perpendicular to the surface. I'm not really drawing the arrows carefully in their lengths, but there is the static friction force also acting this way. Static friction, right? Looks like 3 forces acting on that object. Oh, you know what? I'm not going to use 10 grams. Ooh, okay. Actually, you know, I will use 10 grams. I will. But what I want to do is I want to tell you that there's a way I can test. It's not too hard to do. I can test and get the angle, that critical angle where it's going to start to slide. I've done this test multiple times, and it seems to be, on average, it's hard for you to tell in the video, but on average, it's coming out to about 18 degrees. Okay, for these two surfaces, I've done this about 10 times to get a good average. Collecting data points and all that, you know how that works. So, my critical angle theta, where it starts to slide, is right around 18 degrees. And so, of course, I need a free body diagram. This should be have some axis parallel to that surface. I'll make that the x-axis. And my y-axis is perpendicular to that. Y, x. Okay. Get my forces drawn on my free body diagram. Weight. And now my x-axis is at angle theta with the horizontal. Okay, that's important to realize. And because of the way things rotate in my diagram, there's angle theta between the negative y-axis and this weight. Okay, so that's important to label. What other forces are happening here? I have a normal force in the positive y direction. Keep my symbols consistent here. And I have a static friction force acting to oppose the motion, so it's acting up the ramp, to oppose the tendency to move, I should say, right? Static friction. And in this case, since it is just about to slide, then I know that this is max. This is the maximum friction force, static friction force. And that's worth knowing. It's good for me to know that because that'll help. Now, look at this. One of the important reasons, one of the important benefits for rotating my axes to match this surface, because you can see if I didn't do that, if I just had vertical axis and horizontal axis, then what you would have is one force along the axis and two forces that are not parallel to an axis. And so I would have to break up two forces into x and y components. Well, instead of doing that for two forces, I rotate my axes, clean this up a little bit again, and I only have to break up one force into x and y components. It's less work for me this way. So speaking of the x and y components, I should do that right away. Here's my weight. Duplicate that arrow best I can. And so this has a component in the y direction and a component in the x direction, right? Component in the y direction is about that long. Component in the y direction is about that long, maybe. So this is weight in the x direction. This is weight in the y direction. And there's my angle theta. Okay. And is there anything else I need to worry about? Well, what is the component in the x direction? It's equal to weight, and that's opposite of theta, so this is sine of theta. And this y component is, hold my paper still, weight times cosine of theta. So I know those components, at least symbolically, right? Oh, good. But more than that, I got to recall, weight is mg. Oh, that's going to be useful, trust me. I need to do my, let me use a color that might look a little different here. I need to do my statements of Newton's second law. So sum of forces, right? Sum of forces in the y direction. I like to start with the y direction. I don't know why, but it works. So equal to mass times acceleration in the y direction. But I know that there is no acceleration in the y direction, so that sum is 0. Well, the forces are normal force up and weight down. Oops, not weight down. Weight in the y direction. That guy is opposing the normal force. Those two are what balance each other out. Pay attention here. That sum is 0. Normal force equals weight in the y direction. But I know the weight in the y direction. Normal force equals W cosine theta. But I know W is mg, so this is going to be mg times cosine theta. Okay. That's going to be important in a moment. Let me do the same kind of thing for the x direction now. Sum of forces in the x direction. This is equivalent to a mass times acceleration in the x direction, but there is no acceleration in the x direction. This is not yet accelerating, it's about to. It wants to almost. And Well, what are those forces? Those forces happen to be in the positive x direction. This guy, weight in the x direction. In the negative x direction, my static friction force. And they sum to 0. All right, but I know that weight in the x direction, W sine theta, but I know W is mg, so I have mg sine theta. And my static friction force, well, my static friction maximum is coefficient of static friction times normal force, and that's 0. Okay, so what I'm going to do is look. I'm going to take, because I see a normal force, and I see the answer I want. What is that coefficient of static friction? Well, look right away. Normal force. I have another way of expressing normal force. I'm going to take this and substitute into there. I'm also going to isolate the coefficient of static friction to get it by itself. And we're going to see something pretty awesome take place. But I'm going to need more space. Here we go. Page 6. So here's what I'm working from, right? First I'll do my substitution and keep this very straightforward. mg sine theta minus coefficient of static friction. Now instead of writing normal force, I'm going to write mg cosine theta. And the sum here equals 0. So my substitution was right here. That used to be normal force, okay? Just so we're clear. And well, now I need to isolate my coefficient. So I'm going to, let's see, I'll do this. And then I'm going to have to divide by this business. That's going to be mg sine theta divided by mg cosine theta. Oh my goodness, look what's happening here. Check it out. Cancel, cancel, mg cancels out. You mean to tell me that the coefficient of static friction does not depend on the mass of the object? Doesn't depend on the acceleration due to gravity? Well, no. And that sort of would sound weird if it did, because this depends on this type of surface, nothing else really. But look what we have left. What is the sine of an angle divided by the cosine of that same angle? That's tangent of the angle. I know my angle. So my coefficient of static friction is tangent of 18 degrees. And handy dandy calculator. Keep your calculator in degrees mode for stuff like this, please. I'm going to go tangent. 0.32. That is my answer. What are the units for that number? You're right. There are no units. The units are gone.